Thank you for the introduction. So this is joint work with Roberto Sebastiani from the University of Trento. And as the title says, my work is about the optimization modulo theories. So you're probably familiar with SMT. OMT is an extension of SMT, where we have, so we require the theory to define a total ordering relation less than or equal to 2. And then the problem is given by a pair. So we have a formula that defines the constraints. And then we have a term that we want to optimize. So the goal is to find a model of the formula and of the theory, minimizing the term cost with respect to this total ordering relation. So let's look briefly at an example. So let's consider, for instance, this formula. We represent here on the right the space of the solutions, so of the possible models of the formula. It's the orange region. And then we can have a term that we want to optimize. For instance, here we have minus x plus y. The yellow part are the models that are considered better because they have a smaller value of cost. So in this case, the solution we are looking for is the orange point here, because it's the one that minimizes the value for cost. So this is the problem, the OMT problem. Which theories can we have? So we distinguish between two groups of theories depending on how they are solved. The corresponding OMT problem is solved. So we have theories solved with a so-called lazy approach, which are the theories of infinite precision arithmetic. So we have linear and nonlinear arithmetic over rationals or mixed integer and rationals. Then we could also have other theories. So we have finite precision arithmetic with bit vectors and floating point numbers. These are solved with an eager approach, but the focus of this talk is on the theories solved with the lazy approach. I will briefly recap what the lazy approach is. So the idea here is actually quite simple. So the idea is to make, we have this loop where we make incremental calls to an SMT solver with the formula conjoined with a bound on the cost. So initially we have the upper bound, which is the value of cost in the best model we have found so far, which is initialized to simply. So we ask the SMT solver, if this formula is satisfiable. If it is, then we get a theory satisfiable truth assignment containing a model of this formula. Within this truth assignment, we invoke a theory minimizer that returns us a model which is optimal with respect to the cost in the truth assignment. Then we use the value of cost as the current best upper bound we have found so far. And then we repeat the loop until the formula here is unsatisfiable. At this point, we know that the last model we have found is the optimum for the whole formula. So this is the lazy OMT solving approach. And the nice thing about this approach is that we can actually stop the loop at any point and just return the best model found so far. This is particularly useful with hard distances where we may impose, for instance, a time limit and just obtain a good enough solution. So let's look again at our example. So let's take this formula. We invoke the SMT solver. It will return a truth assignment containing some solutions of the formula. And within the truth assignment, we invoke the minimizer returning us this model, which is optimum for the current truth assignment. Then the value of the cost in this model is used as a current upper bound. It's conjoined with the formula, and we repeat this process until the formula is unsatisfiable. So the main point we make is that this loop is actually suboptimal because the truth assignments returned by the SMT solvers are total, meaning that they assign a truth value to every atom in the formula here. But in principle, for a truth assignment to satisfy the formula, we would only require it to assign one true literal per closed list. So our goal is, instead of finding total truth assignment, we want to find partial truth assignment, sorry. And ideally, we want small partial truth assignments, because small partial truth assignments correspond to a larger solution space within which we invoke the minimizer, meaning that we find a better current upper bound, which allows us to impose a tighter bound on the optimum, and this will lead to a faster conversion to the global optimum. So the question is, can we exploit partial truth assignments for optimization? So the answer is yes, and let's see how. For instance, starting from this total truth assignment here, we can see that some of the literals can be dropped. For instance, this literal here is not necessary for it to satisfy the formula, because if we remove it, then this clause is still satisfied. And by removing it, we actually enlarge the solution space, and we find a better optimum. We can iterate this process and look, for instance, at this constraint here. We can remove it. This clause is still satisfied. We have enlarged again the solution space and found a better optimum, which in this case is also the global optimum for the problem. But in general, this helps anyway because it allows us to add a tighter upper bound and faster converge to the optimum. So this is the algorithm that is the same as before, with the only difference that we add this line. So once we know the problem is satisfiable and we get a total truth assignment, we invoke some procedure to extract from it a partial truth assignment, and then invoke the minimizer over it. So how do we implement this procedure? Because starting from a total truth assignment, depending on the constraint we choose to remove, we may end up with different partial truth assignments with different values for the optimum solution. So the simplest thing we can do is just try to remove the literals in any order. So we iterate over the literals of the total truth assignments, and then check if they can be safely removed from it, so that all the clauses in phi are still satisfied. If so, we can remove it, and then iterate until we look for all the literals. This is nice because it's very simple, and it works for any 1T theory. The only problem is that it's blind with respect to the optimization. So we are not really taking into account the fact that we are optimizing some cost. And this has a drawback, that is, we may end up removing unnecessarily constraints, meaning that we can remove a constraint, but still the optimum model for the truth assignment is the same. This not only is useless, but can be harmful because it can prevent the removal of other constraints from the truth assignment. So what we propose is some optimization-aware reduction for truth assignments. which takes into account the setting of optimization. In this reduction, it's the theory minimizer that suggests the constraints that are currently limiting the optimum in the truth assignment. Meaning that these are the constraints that, if removed, will likely lead to a better model in the truth assignment. So this is the procedure, so that minimizes, that reduces the truth assignment. So we start from the total truth assignment, we find the minimum, and then ask the minimizer which are some of the literals which we should drop for improving the optimum model. If we check if they can be safely removed, so the partial truth assignment still satisfies all the closest formula. If so, we remove, we invoke the minimizer again, and then iterate this loop until we analyze all the literals, or we don't have any more meaningful literals to drop. So how do we identify these constraints that are limiting the optimum in the truth assignments? The general idea is that we want to find a possibly minimal complete set for the truth assignment conjoined with the bound on the cost. This formula here is unsatisfiable because we know that M is optimum for cost. So there is no better model in the truth assignment for cost. So a complete set is a subset of the constraints that causes the unsatisfiability. So this is the general way. The only problem is that it can be costly for some theories. But for some theories, we can have actually this information for free from the minimizer. And we'll show this for linear arithmetic over the rational or mixed integer and rational array. So let's consider first the linear arithmetic over the rational. We know by the properties of the simplex method, which is used to solve it and to optimize the model within the truth assignment, that the optimum model always lies on a vertex of the polytope defined by the truth assignment. And also we know from the algorithm that we can get the constraints defined in such vertex for free from the tableau of the simplex algorithm. So we can just ask the theory solver and minimizer, which are these constraints. So for instance, in our case, these are the only two good candidates constraints to drop. Because for instance, if we drop these, then the optimum model wouldn't improve. So we can choose either of them if they can be safely removed. If we remove it, then we get the better optimum. And then we can check again. We can remove this constraint here and then end up with the optimum. So this is for rational arithmetic, linear rational arithmetic. What about mixed integer rational arithmetic? In this case, we don't have anymore the nice property that the optimum model is always on a vertex, because for instance here, the vertex might not be integer. So in this case, the optimum model is this point, but we can reason on the continuous relaxation of the problem so that we find the rational optimum and still identify the constraints that limit it. This is a good heuristic because the relaxation guides the search for the integer optimum. So if we remove either of these constraints, then we will improve the optimum of the relaxation and likely also the integer optimum. So we can use this heuristic, which is cheap, much cheaper than reasoning on integer arithmetic, and still have like an effective way to reduce the truth assignment. So let's look at some experimental results. We implemented this in the Optimazza OMT solver and evaluated it on two different sets of benchmarks. So for rational arithmetic, we have strip packing benchmarks and temporal planning benchmarks. We also modified the strip packing benchmarks with mixed integer and rational encoding, and also to show that this works also with combination of theories, combining rational arithmetic with arrays. And we compare the different truth assignment reduction strategies in terms of running time for optimum solving, but also for the instances that time out, we get the best model found within the time limit of 1200 seconds, and compare the legacy OMT schema with the different truth assignment reduction strategies in terms of the upper bound. So these are the results on the temporal planning benchmarks. So on the first row, we compare the reductions in terms of running time. And on the second row, we compare them in terms of the best upper bound found. On the columns, we compare pairwise the reduction. So we have the no reduction compared with the basic reduction. And we have the no reduction compared with the guided optimization aware reduction. And finally, we compare the basic reduction with the guided optimization aware reduction. So we can see that using either of the reduction improves the running time generally, sometimes up to twice as fast. And also the quality of the best upper bound found within the time limit. You can see that there are a lot of points below the bisector here. So which means that with using either of the reduction, we obtain a better optimum in the time limit with respect to not using the reduction. In this set of benchmarks, there is no clear winner between the two reductions. So also the basic one works well. Instead, on the strip packing benchmarks, we have, so here, all the instances stand out. So we only compare in terms of the best model found within the time limit. We can see that using the basic reduction does not really improve. So we get more or less the same upper bound. Instead, using the optimization aware reduction, we get much better quality results in the time limit. And also, if we compare the two, it's the winner is clearly the guided optimization aware reduction. So this was on the LRA strip packing. We also evaluate on the mixed integer and rational arithmetic, and we get similar results. So also the reasoning on the continuous relaxation is shown to be effective here. So this was the main results. So concluding, we have shown that exploiting partial assignments in OMT is a promising direction, both for optimal and anytime OMT solving. And we have also shown that using optimization aware reduction is very effective in practice to converge faster to the global optimum. So as future work, we plan to investigate more doc optimization aware for other techniques for other theories, and also explore the interaction of other reduction techniques for truth assignments, for instance, entailment-based truth assignment reductions in the context of OMT. So that was all, and this is the